So this leads us to the next topic of this chapter, flow nets. For this course, what you're required to know is to use flow net to solve seepage problems. So basically, if you're given a flow net, can you use it to calculate seepage quantities, head at any location, pore pressure at water pressure at any location, and the factor of safety against piping or heaving? First, what is flow nets? As I mentioned, flow nets, it's a graphic illustration of how total head or energy distributes as water flows through soil. In essence, it's a solution. It's a graphical solution. It's approximation to Laplace equation, and it's used for practical engineering purposes. So shown on this slide are two examples of flow nets. On the left is a flow net of seepage around the sheet pile. And on the right-hand side is a flow net for seepage problem underneath a hydraulic structure like a concrete dam. And to introduce some of the basic concepts of flow nets, I'm going to use this left picture here. So flow net around sheet pile. So I'm going to explain what does the line or all these lines represent on the flow net and how do we use them. So first, very briefly, the sheet pile, this is a retaining structure basically. If you look at this picture here, so you have all these steel sheets, they are interlocked with each other. So they create basically a flow barrier that retains the soil on one side and then blocks flow from the other side. And so some terminology, so we're going to call this is the length direction. So this is the length direction. I'm going to use this capital letter L to refer to the total length of this hydraulic structure. So that's L, total length. And then the analysis we're going to look, all these analyses are for just one cross section, 1 unit length. So we're going to look at just 1 unit length and see how water flow around this 1 unit length of sheet pile here. Okay. So this is a complete flow net of around this unit length of sheet piles. And some quick definitions here. So this is, of course, that's your structure, sheet pile. And then on the left-hand side, we have a higher water table. So this is water level H1. So that's our upstream. And on the right-hand side, it's a lower water table, H2, that's a downstream. And then we have, this is our permeable soil layer. And that's where water seeps through. So that's permeable soil. And then we also have this impervious layer or impermeable layer. And water cannot penetrate this impermeable layer. So water is going to flow through this permeable soil only. And then I'm going to explain all these lines in the next few slides. And then also, this total head loss is defined as the difference between upstream and downstream water level. So capital H, we call it total head loss. So water is going to enter through this upstream soil layer here, and then it's going to exit on the downstream side. So it's going to flow through the permeable layer here. Okay. So that's some basic definition of this sheet pile flow net problem. Then we're going to look more details about this flow net. So a flow net consists of two basic type of lines, two family of lines. And the first one is called the flow lines. So flow lines basically is where water travels. So water travels from upstream to downstream impermeable soil along flow lines. So if I show this flow net again, just isolate two types of lines here. So this blue line highlighted on this slide, this is the flow line. So think of this as the path water takes to travel from upstream to downstream. So that's the flow line. So water does not flow through, in straight lines around your hydraulic structure, but it's flow around this along this curve we call flow line. So that's the first type of lines in a flow net. And for that given flow net, for that example, we have this number of flow lines here, 1, 2, 3, 4, highlight here on this slide. So that's the flow lines in the flow net. And the second family of lines is what we call equipotential lines. So equipotential lines, basically, on these equipotential lines, the potential or the head or energy, they're all equivalent. They're referring to the same thing. So on an equipotential line, the potential is the same. So if you look at this, again, I'm isolating just two curves, two lines here. The first one is that flow line we just introduced. And then the second line, the red line highlighted here, is one equipotential line. So equipotential line, as the name suggests, any point on this equipotential line has the same potential. Okay. So let's say these 2 points here. If you put two piezometers at these two locations, the water table inside these two piezometers are going to rise to the same height because these 2 points, they possess the same potentials. So remember, the total head is the height of the water table inside the standpipe above your data or above your reference data. So if they rise to the same height, that means they have the same energy. Okay. If you put another standpipe, say at the third location on the same equipotential line, it's going to rise to the same point, same height. Okay. So that's equipotential line. And for a given flow net, you have a number of equipotential lines. So they're all highlighted in red on this slide here. Okay. So all these are equipotential lines. So these red curves. Okay. So these are the two basic type of lines in a flow net. And then some additional definitions. So flow channel is basically the strip between any adjacent flow lines. And NF, we call the number of flow channels in a flow net. Again, I'm going to use this example here. So for this example, this is the flow channels. So remember, this is what we call flow lines. So there's another one. Flow lines here, flow lines, and flow lines. Okay. So this is the strip between any two adjacent flow lines. So that strip is a flow channel. Okay. So think of this flow channel as a pipe. So water flows through this flow channel from upstream to downstream. And NF is the number of flow channels. For a given flow net, you can read that number of flow channels from the flow net. So for this one, we have 4. So number of flow channel for this flow net is 4. So we have 1, 2, 3, 4 here. And then there's this definition of potential drop. So potential drop is the head loss between two adjacent equipotential lines. So we call it delta H. And it's important to keep in mind that for a given flow net, potential drop delta H is the same for any two adjacent equipotential lines. Okay. And this delta H, because it's the same for any two adjacent equipotential lines, so delta H can be calculated as the total head loss capital H over the number of potential drops. Okay. We call ND. So again, use this flow net example here. So potential drop is the head loss between two adjacent equipotential lines. So from the first one to the second one, so we have one potential drop, delta H. And then for this flow net, we have 1, 2, 3, 4, 5, 6 potential drops. So ND for this flow net is 6. And then the small delta H is basically capital H. So remember, capital H is the head loss from upstream to downstream. So that's a total head loss divided by ND. Okay. So it's the same again between any two adjacent equal potential lines. So they're all delta H here. So that's the potential drops, delta H. And then there's this definition we call a flow element. So flow element, so as highlighted here, basically it's a square or rectangular shaped, approximate square rectangular shaped element that is bounded by two adjacent flow lines and two adjacent equal potential lines. So for this flow element here, we call B the width of the flow element. So that's perpendicular to the flow direction. And L, the length of the flow element, that's parallel to the flow direction. So that's flow element. And delta Q is basically the flow quantity in and out of that flow element. So they are equal by just continuity of flow. Okay, so finally, some additional basic rules about flow nets. So first, the equal potential lines, they intersect impermeable boundaries at 90-degree angle. So if I go back to this slide here, so all these dashed lines are equal potential lines, and they intersect the impermeable layer, that's the layer at the bottom, at 90-degree angle. So that's equal potential lines. And for isotropic soil, equal potential lines intersect flow lines at approximately 90-degree angle. And for this one, these two lines, they intersect at approximately 90-degree angle if the soil is isotropic. And also, with the geometry of a seepage problem given, you immediately know these four lines. So you immediately know two equal potential lines and two flow lines. So I'm going to show this with, again, the same flow net. So for this flow net, once you're given this flow net, immediately you know two equal potential lines. So the first one is along this upstream water table. So all points on this line have the same total energy or potential. And same for downstream water table here. This line parallel to downstream water table. And also, you immediately know two flow lines. So these two flow lines are along impermeable boundaries. So the first one along this sheet pile is actually an impermeable boundary. So the water is actually going to flow along this sheet pile. So that's one flow line. And the other one is FG. The water is going to flow along this impermeable boundary FG. So you know that this is a flow line as well. So you immediately know these two flow lines as well. In example one here, so this is just a very simple example. You're given this flow net. This is one of the two flow net pictures I showed in the previous slide. So you're asked to determine NF and ND. Okay. So NF, remember that's the number of flow channels. So if you look at this flow net, so we have 1, 2, 3, 4, 5. So flow channel, again, so that's a channel bounded by two flow lines. So that's one flow channel. So for this flow net, NF equals to 5. And then ND is the number of equal potential drops. And so from one equal potential line to the next, this is 1 delta H. And then you count how many are there, and that's your ND. So 1, 2, 3, 4, 5, 6, 7, 8, finally 9. So for this flow net, ND equals to 9. Okay, that's a very simple example just to read these two numbers from a given flow net here.